Hello and welcome back. In this session, we are going to learn how to invert binary tree using Python. Okay, let's quickly go through the problem statement if you didn't get a chance to go through it in the Java video. Okay, statement reads as invert a binary tree, and we have sample input here. 4 is the sorry, 4 is the root, left hand side subtree, and 2 root 1 and 3 leaves, and right hand side we have the 7 as the root node for leaves 6 and 9. Okay, probably it is more clear from visual here. And then if we invert it, what happens is the main root remains same 4, because if you take a mirror image of it, it doesn't change, right? And then anything on the right hand side comes to the left hand side, anything on the left hand side goes to the right hand side. Okay, the 7 and 2, they are also root, so they also they change the, like if it was in the right hand right subtree becomes left subtree, and left subtree becomes right subtree. So the root of the right subtree, so that doesn't change, right? Because it doesn't have two elements. It's a one. If it's one, just remains one, right? But the entire structure changes. Structure change. They swap their position. But if you see only in the substructure, uh, their position has not changed. Okay, but their position in the global structure has changed. Now for 7 in the given input, um, you have 6 as a left leaf, and then 9 is the right leaf or right node, right? So that also gets reversed. Is it got reverse here, and then that is true for the right subtree. In the original tree, that's the left subtree. So 3 takes 1's place, 1 takes 3's place. And if you see it in a higher level, if we do more like a node root, left node root, right node visit, it becomes 1 2 3 4 6 7 9, and for the inverted one it becomes 9 7 6 4 3 2 1. One is ascending order, another descending order. It's a binary tree, so elements are in sorted order, and time complexity and space complexity both are order of n, because for time complexity we visit all elements only once. We don't have to visit twice. So all well, even if we visit twice, probably it'll be 2n. It's still order of n, but not definitely order of n square, because we don't have to do that, right? It's not, yeah, it's order of n, all visiting at once, where n is the number of nodes in the tree. And space complexity, uh, in the worst case, it is order of, yes, it's height, and then the height can also become like it can take extreme form. Like you could have all nodes going all in the left, and it can also go all in the right continuously, meaning uh, it can already be, well, let me show it visually. Like now we have in the inverted one 4 7 9. Instead of that, it could be 1 2 3 1 2 3 4 6 7 9, all of them. So that means it's taking all n going in this direction, right? And it can also be in the right direction. Like if we start from 9, and then it can go to uh, well, yeah, or it could start again from, it has to start from yeah, it's in inverted. It's to it could start from um, 1. It could start from 1, uh, and then if it starts from 1 and the right hand side, which goes, that becomes 2. But if it's on the left hand side, it has to start from well, it can start from 1. If you go to the right hand side, it should start from 9, sorry, because we'll be visiting, if we go to the right hand side, we need to visit the leaf first. It'll be all a right leaf, so we need to visit the node first, right? So that means, yeah, 9 has to come first here. So basically the point is, either it can be go see the movement of the cursor. Either it can go this way all the way, or it can go on the right hand side all the way that way. Okay, if it goes that way, it will still be order of n. That's all. Well, the thing is, when you process it, internally we'll be using storage, and that storage has to take care of all of these things basically. Since we are using recursion, it uses stack internally and then remind it to recurse all the way, because it's you have to recurse like n all the way n times. It may not be shorter, but if the tree is more like a balance like this, then it'll be much quicker. Actually, you'll find leaf nodes and the node the root like that. But if it's like a one-sided completely, and it'll recurse more number of time. Okay, that's the main idea here, right? Let's not waste any more time. We just we're minimizing that, and we are going to see the pre-typed program again, because if we start typing it will take longer, and that maps the video size. All right, this is the Python. We earlier we saw Java, this is Python. Okay, I have a constructor here. This is a class, small little class. See how short the code is. I didn't need a getter setter. I didn't need to declare variable, anything like that. Everything is done in one shot. See def init, that's my constructor. Self, to mention that this is the class method. This is method associated with the class. And then I have data, I have left node, I have right node, and then I have given initial value. Okay, nothing is passed, data is going to get 0, left node is going to get none, right node is going to get none, which is like a null in Java. Okay, and then I assign them self, meaning this is a class variable, self data. When I say that, okay, so this is also the declaration actually, and then its type is inferred from whatever types comes with this data on the right hand side, whatever is passed, right? So self data is equal to data. Self left is equal to left, self right is equal to right. Okay, that's how you construct the tree node. All right, and invert logic, if root is none, we pass the root. If root is none or null, obviously in Python is none. If it's none, then we return none. We don't have to do anything. That means. Otherwise, in a variable right ref, we invert the right subtree and store in right ref. We invert the left subtree and store in the left ref. And then in my roots left hand side, left subtree, I assign the right reversed, and then roots right hand side, I assign the left reverse. Okay, that means everything got reversed except the root element, which doesn't have to be reverted, because if you take a mirror image of it, that's the center element, right? And then we return the root element. That means basically we are returning the entire tree. Return the pointer to the root, right? That means if you point to the root, you can easily navigate to other elements. So well, in the next line number 17, we start navigating, because we need to print them. If that's actually a node, that node is actually a root node here. Print uh, print and then tree. Okay, if the node is none, if that, let's say if the well in the first atom is it's a root. Okay, we pass the root, so initially root comes. If root is equal to none, we don't have to do anything, we just return. If that root is not equal to none, then we check the roots left, check whether it's none. If it's none, we didn't have to do anything. Okay, and we print the data, and then we check whether right exists or not. If right exists, we print the right. Okay, but if it's not, if it's not none, then it might have its own subtree, right? So we then we do recursively. We will print tree node dot left, and then this entire structure here, line number 17 to line number 25, will be applied again, because that can be another subtree, right? So subtree and node might be yeah, well, that one we checked here, and node may or may not be none. Node is not obviously none here, we check that. And then when it comes here, we'll check its left subtree and its right subtree. So it keeps going until it finds the leaf elements. Okay, so if you see this order, we are checking that the left subtree first, and then the node element, and then the right. So it's always going on visiting left node right, left node right, and it comes with the entire structure. All right, in the main, leaf 1, leaf 2, leaf 3, leaf 4, we're creating that by creating instance of the tree node. If you see here, leaf 1, 2, well, look at the original 1369, 1369, and then left node is 2 is the root, right? And then leaf 1, 1 and 3, and the right node is 7 is the leaf over here, 7 root, and then leaf 3 and leaf 4, which is 6 and 9. Okay, and then let's minimize this one, and then root is actually 4. Well, I might need to just visit that. Who knows? All right, here 4, right? 4 over here, first figure, and then left subtree, right subtree. That's it. All right, left subtree, right subtree, and then we print the print tree. This is I can just do print because we have to navigate it. Print root. Okay, first we print uninverted and then we print new line, and then we print the, well, we didn't print, we first invert it, assign to variable, and then we print the inverted, we print the uh, inverted tree. Okay, and then last two lines we are familiar with those. Okay, we're checking the name, calling main call, and then main calls other structures like tree class, other methods which is needed. Now we are, well, we didn't have anything to save, so I'm just going to, I think we didn't change anything, so I'm going to just quit here, and I'm going to just run it. Python invert dot python. Okay, beautiful. Well, it has to be beautiful because it has a pre-typed program and already I have tested it, so no surprise. But we were going to validate it, okay, because that's the essential thing. We explained it, now we're going to validate it. Okay, that gives us confidence that it actually worked correctly. Okay, so visit order is left node. Let's close that. That's not required. Left node, root, right node, and this is the left structure we visited. Then we visit the root 4. Okay, 4 is exactly in the middle over here, and then similarly in the right hand side 6, 7, 9, and then we visit the inverted one is 9, 7, 6, 4, 3, 2, 1. Okay, inverted, and we see that there's an ascending order, this is in descending order. That's very nice. We saw the output, the program is working correctly, and this completes our binary tree reversal implementation using Python.